around it. It doesn't really make sense to me because it's like describing it as a 2D plane.
Well, it's not a 2D plane, but that's a good question you could ask him if we get time to get to that.
You haven't like over here or something.
Hold on, let me see. Okay, apparently me tripping over the cord was what I needed to do. Great. Okay, so let me see if I can find a good spot here. It doesn't go very wide, so can I have you guys find a spot over here, just so you know, all looks like we're here. Of course, nobody wants to sit right up front. That's fine. It's he'd be awkwardly close. And there you go, sit right there next year. Oh, okay, so we have about 5 minutes. So, yeah.
Me and my friend, the research firm is not.
Fantastic.
Do you guys have a Google Classroom?
We do.
Oh, can we join?
Sure. Let me throw the code up there really quick. Oh, you're gonna sit right there, aren't you?
Who's gonna stop us?
Nobody, I guess. Well, welcome. We actually have a guest speaker today who's an astronomer. Well, he's a physicist and he does stuff with astronomy. So here is the Google Classroom code. You want to go ahead and join? Do you have the questions up?
Yeah.
So we're going to kind of let Charles go through the questions that we have. We're going to start with kind of the occupation and stuff. Now, if he says something and you kind of have a follow-up question, it's okay to ask. I'm just going to ask that you raise your hand just so we can, you know, make sure that we get to everybody. We want to try to get through the questions that we had on there. So if we go back and look, did you get in?
No.
Okay. So we tried to prioritize our questions during the last meeting. So can you still see the code or you got it?
Give me 1 more second. Oh, okay. I'm good.
You got it? Okay. So the questions that we came up with, obviously the education, we're going to kind of go through those questions. And then the questions in yellow are the questions we're going to try to hit first. And then if we still have time, we can maybe kind of get into some of the green questions. Okay. But if something comes up and you have a question, let's just raise our hand just so, you know, we can give you an opportunity to ask your question. The Conftell speaker is pretty good. It should pick you up wherever you are in the room. That's why the school bought them. So it should be able to pick you up anywhere in the room. I'm going to go ahead and load up our Zoom here. All right, so at least we'll get a warning before he pops in here. Okay, be right back.
Where's David?
Don't pick your nose if you're on the camera, obviously, because he will be able to see everything that you're doing. You know, pick your nose.
Who's gonna stop me?
I saw some interesting things that people did on Zoom unconsciously when I was teaching on Zoom. Yep, nothing too bad. Charles, come on, man. All right. So he should be popping on. I did confirm with him today, so he should be popping on here in just a second.
What is that?
I did talk with the gentleman at Civil Air Patrol that we kind of talked about during the last meeting. So he is planning to come, I think next week. He might pop into our meeting next week to kind of talk to you guys about what he does with Civil Air Patrol and possibly discuss some ideas on telescope parties or model rocket launches that we can do together with them. And then I'm going to go to one of their meetings to talk to his cadets about inviting them over to do star parties or launch model rockets with their club. So that's coming up.
His cadets are gonna join us.
Yeah. So Civil Air Patrol, if you're not familiar, is the civilian component of the Air Force. It's basically like kind of like ROTC here, but it's for the Air Force and it's done outside of school. So most of the kids are like junior high, high school, and it's a really good program because you can earn scholarship money. If you decide to go into the military, there's some perks. You can get like start out at a higher rank instead of starting at the bottom of the pay scale there. So it's really cool. Yeah.
I have a question. Are you guys still allowing a shirt order?
Yeah. So that's the other thing. Yeah. If you guys haven't ordered a shirt yet, I got yours. If you haven't ordered a shirt yet, if you guys could try to get those in by Friday, so I can put the order together. Here we go. You try to get those in by Friday. All right. So let me jump in here.
Hello?
Hello. Oh, we can't hear you. I think you're muted. Can you hear us okay? I think your microphone's still muted.
Okay, there we go. I'm sorry, I couldn't find my mouse cursor, and so I didn't know.
Hello. I don't know if you could see me. I'm the teacher you were emailing me with. So this is our astronomy club. Sitting in front with the cool hair is Charles. He's our club president, and then over here is Diego. Tesla's not here today. Okay. So we have a bunch of students in our school very interested in astronomy. Obviously, we got matched with you for Skype-a-Scientist. So two cool things about our school, and I don't know if I mentioned this in the email. It's a very old school. It was I believe it was the first community college in the country. Was on the 4th floor of our school. So we have a planetarium in our school, and we also have an observatory on the roof of our school. It's in need of repair, but it is there. So
that's awesome.
A lot of kids are interested in astronomy here. So we're really thankful that you could join us today. First thing I'm going to have you do is, if you don't mind, just kind of introduce yourself to our club, and then our club president Charles has got some questions that we prepared to kind of go through with you.
Oh, okay, sure. I'm Dr. Victor Taveras. I'm originally from the Dominican Republic. I was born there, and then I moved to Rhode Island when I was a year old. So I grew up in Rhode Island. I went to the University of Rhode Island, and I studied physics and mathematics. They did not have an astronomy there. And I went to Penn State for my PhD, and I did research like in quantum gravity. So like, but it's all theoretical physics. It wasn't like observational or anything. But I did some research in like with quantum cosmology and quantum black holes and mathematical physics. And then I did like a postdoc at LSU for a couple of years doing research. And then I switched to full-time teaching. And so I've been here. This is my 12th year now. I teach our astronomy classes. We don't have an observatory or a planetarium, but I teach our astronomy classes, or like all level physics classes, and whenever they need me, I also teach some like technical math and some engineering. This is a community college, so there's like a wide range of students here, and like a wide range of programs. But it is it's pretty nice. I'm probably about 6 hours straight south from you guys. I'm in the part of Kentucky that's like I could see Illinois almost from here. But that's where I'm at, and like a quick background on where I've been. But I'd be happy to share more.
All right, go for it, Charles.
Okay, so I have a question that I just came up with. So
Okay.
Astronomy, right?
Yes.
So how exactly do like the courses progress, and what does it progress to? Like, what info do you teach?
Here, because it's a community college, there's there's mostly just courses for the non-science majors. People who just need to take a course for their degree and they need to take a science course and they don't want to take chemistry, so they take astronomy. But occasionally there's usually a few students here who start here and then they transfer to like a 4-year college like Murray State or University of Kentucky, and they do have interest in astronomy or some other science. But here it's mostly people who are kind of interested, or they just want a science class and it's not as scary as the others. But the course we do teach is like on the solar system, and it's in our system we offer like a intro to astronomy course. It's like Astronomy 101, and this course is a little bit more like comprehensive than that. We talk a lot about how telescopes work and like the how do we discover other planets and things like that. So it's a little bit more advanced. But as far as where we're at, that's what we offer. We also have a class on stars and galaxies. And whenever my supervisor lets me, we also have a class on astrobiology. So, like the search for life in the universe. But it's a fun course, but of course there's more questions than answers there, which is what makes it so fun. But as far as astronomy, those are our courses. I teach astronomy at night, like Wednesday nights, and also online. And so with the on-campus class, whenever it's possible, we try to go outside with the telescopes and observe things. So I'm teaching tonight, but it's raining here today, so we're not going to do that. We're just going to stay inside.
All right, I'm gonna start going down the list now. So the first question here is, what's your favorite astronomical phenomena?
My favorite astronomical phenomena, probably because when I was working on my PhD, I spent a lot of time on like black holes. I would have to say black holes, because I did a little bit of research related to that, and they're still pretty cool. And like just recently, I don't know if you guys are aware, we were able to photograph a black hole, like with not a regular photograph, but with like a radio telescopes to image a black hole like 2 years ago. I still think they're pretty cool. So that I would say that's my favorite phenomena there.
That leads up perfectly to the next question. Do you have an idea on what black holes are exactly?
Not we kind of understand like how they form, like what they behave like, but it's still kind of confusing. So I don't know if we would say if we understand what they are exactly, because there's still a lot of unanswered questions there. So I would say there's still a lot to know, right? I would say there's still a lot for us to know about them.
Can I jump in with a question really quick? So we can't see black holes because they absorb all the light.
Mm-hmm.
So how do you detect a black hole?
That's a good question, right? It's like seeing a shadow, because you can't see them, but you can see the stuff around them. All right. And so that's when people talk about seeing black holes, that's really what they mean. And so it's kind of like if someone was standing in front of a light, like a bright light, you can't see them because of the glare, but you can kind of see like their shadow and the light around them. So it's kind of like that. You're you're not so you're not seeing the black hole directly, but you're seeing the stuff around it and more of like the shadow of the black hole. It's kind of weird.
Do you think a black hole is a vortex to another universe?
It's possible. I would say probably not. From my experience, I would say probably not. But if you study general relativity, which is I'm not sure how much you guys know, but general relativity is like our best theory of gravity, right? It's basically what it is. And it describes things like black holes where gravity is very, very strong. And if you look at the equations of general relativity, that people call them Einstein's equations, and you try to solve them, you try to solve those equations, you get really weird solutions to those equations. And they describe really weird things. And one of the possible solutions is that like what you see as a black hole is like an opening to a tunnel to another universe, what they call a wormhole. So this is like exactly what you're describing, right? So the short answer is it's allowed by general relativity that these exist, but we haven't seen them. And when you study them further, they're unstable, right? So you would need some exotic material to hold them open. Like if you wanted to send a spaceship through one, you would need some exotic material to hold it open so that you can make its way through. But according to Einstein's equations, they're allowed. It's a possibility. Whether they're realized in the real world, we don't know.
Yeah, since we're on like the topic of black holes being like wormholes and stuff, do you think a white hole could exist?
A white hole is also a possible solution to Einstein's equations, but I'm not sure. Well, first of all, we've never seen one, right? And a white hole is the opposite of a black hole. But I'm also not sure that they would be like stable. Like if one existed out there somewhere, if it would last long. So sorry for the vague answers, but we just don't know.
So we have, I mean, I think everybody here's heard of a black hole before. So maybe some of our members that aren't familiar with a white hole, could you maybe describe what they are in theory?
Yeah, so in a white hole, so if you understand what the black hole is, just think of running. I think the easiest way to imagine one is to think of time running backwards. And so in a black hole, if material falls into the black hole, it can't escape. As time progresses, you can only go further in, right? The event horizon, what you think of normally as the surface of a black hole, is like the point of no return. Once you enter that, you can't escape. So a black hole, a white hole, excuse me, is the reverse of that, right? It's some object where material's coming out, right? Instead of material going in, like in a black hole. And it's weird to think that something like that could be stable. But from when you play around with Einstein's equations, that pops out as a possibility. Whether they exist or not, we don't know. right? But that's essentially what a white hole is. It's the opposite of a black hole. Instead of material coming in and not being able to come out, material goes out in the other direction. We don't know if they exist or not.
Yeah, another question. So, do you know what the axis of evil is?
In like what context?
Astronomy.
It sounds familiar, but I would you would have to refresh my memory on it.
So it's basically a name given to the apparent correlation between the plane of the solar system and aspects of the cosmic microwave background. That's the Google.
Oh, okay. Sure. So what's your question?
I wanted to know what your thoughts were on it because I've heard some stuff about it, like how if scientists did more research on it, it could completely destroy like 90% of what we know on space. But I don't know if that's true or not.
Yeah, I'm unfamiliar with that, so I don't know if I could confirm those claims or not. I'd have to look into it a little bit more. But yeah, so I'm not sure where that argument is going.
So next question. One of our members is curious how rogue planets are formed.
Oh, that's a good question. So do you all know what rogue planets are, or should I like very quickly go over it, or?
We have some new members, so go over it.
Okay. So so rogue planets are, so we have our solar system, and in our solar system there's the sun at the center, and you have the 8 planets orbiting the sun, right? And then a bunch of other stuff, comets, asteroids, dwarf planets. And we've discovered thousands of other solar systems. We've discovered planets around other stars. And so now we think that most stars have planets around them, right? And when you learn about how solar systems form, you start off with a cloud of gas, which we call a nebula, and that cloud of gas, it can contract by the force of gravity, and as it collapses, you form the sun at the center, and you usually have a bunch of planets orbiting the sun. And what happens during the formation of a solar system typically is that the giant planets like Jupiter, in our case, they form first, right? And so we have plenty of we have some evidence that Jupiter formed first, and then Saturn, and then the other gas giants. But what happens is that as the solar system forms from a gas cloud, it starts to collapse, kind of like because if it's rotating slightly, it collapses in this direction. Like if you take a ball of pizza dough and you spin it, it flattens this way and spreads out this way. So the solar system is like the same way. You form from a cloud of gas, and even if the gas cloud is rotating just slightly, it collapses this way and spreads out this way. And so the planets form in this disk. But there's a lot of material in the disk. And as the planets form, they plow through this material and they scoop it up and they get bigger and bigger. What happens, or like what we know from computer simulations, is that through mostly gravity interactions, as the planets are forming, they slowly move outward, right? And So you can imagine a big planet like Jupiter forming, and it's plowing through this cloud of stuff. Well, sometimes these planets, they interact with other planets, right? They either crash together and clump to make something bigger, or their gravity will fling something into the sun or out of the solar system. It's kind of like if you if you imagine like two people on roller skates and they're heading towards each other and then they lock arms. You can fling the other person this way really easily. And so, while the solar system is forming, you get a lot of these interactions. And sometimes debris is flung inward into the sun or into the inner solar system. And sometimes it's flung outward, right? And so we think that a lot of these rogue planets probably formed during the formation of some solar systems, and they just got flung out in the early stages of that solar system forming. So now we think we've observed quite a few, and by like doing statistics, we think that there are probably like trillions of rogue planets just floating around, like in the space between stars. But I think that's probably the most likely explanation for how they got there. I don't think they formed there, but they were flung outward from a solar system. Does that answer your question, or?
It made it clear, yeah.
Oh,
Is it potential that like Earth could become a rogue planet? Or is it possible?
it is possible, but the chances are very, very small. When people do simulations, they put the laws of physics on a computer and they simulate the motion of the planets. I think our solar system is stable. I would have to look up the exact number, but I think it's stable for like hundreds of millions of years, right? So the planets, the major planets, the way they are now, are probably going to be this way for a very long time. But in the early solar system, it was a lot more crowded. There was a lot more material moving around. So these types of interactions were very common for planets to just get flung out. But I think right now we're safe.
Okay. So I want to ask you more about your education now. So you came from a low-income family, right?
Yes.
How exactly did you like have the money to pay for school?
I did not. The short answer is I did not. And to be honest, I still have some student loans from when I was an undergrad. And I had good grades in high school. So I did have some scholarships that would pay for most of it would pay for things like tuition, but not like room and board and stuff like that. But then, I also got in trouble. I had bad grades. And so I lost my scholarships for a few semesters and had to take out loans. And so I still have some of those, unfortunately. But for undergrad, it's complicated, but there are potential sources of funding. For graduate school though, if you're going into like a STEM field, chances are your school would be paid for. Like if you go to school in math or physics or astronomy, some other science, chances are that your tuition is paid for, and the way it's done is that department uses you as labor, and so you would typically be like a teaching assistant for the introductory courses, right? And if you do that, you run labs or or grade homework or something, they'll pay you a stipend and they'll pay for your school. So for most STEM fields, like if you're gonna get like a master's or PhD, it should be paid for by the department if you go to like a state school or a bigger school.
Like a work study program, pretty much, kind of.
Yeah, so the way it worked for me in particular was like the first 2 years, the department because everyone who's a science or engineering student has to take physics, like a few semesters of physics.
Right.
And so the first 2 years, the department would have us be teaching assistants. And you would have a few labs to cover. And if you did those, you ran the labs and you did the grading, they would pay you a stipend and they would pay for your school. And then after 2 years, it was expected that you'd be in like a research group, you'd have an advisor, and you would be doing research with them towards your PhD, and that they would pick up like the tab and pay you your stipend, and so forth. At least that's how it worked for me, at least. But I think the experience is pretty similar for most STEM fields. In humanities or some other areas, it's different. It's a lot more difficult.
So another question some of our members wanted to know was, what was the hardest part of your education?
The hardest part was probably when I was a sophomore as an undergrad. To believe it or not, you would think I would say when I was a PhD student, this was difficult, but like learning how to do college, right? Basically, is like how to be a good student, how to study, take notes, because like a lot of times, it depends on where you go to school. It's different going from high school to college, and a lot more is expected from you in college, and like you learn how to be more independent and like basically teach yourself, right? And so that like requires a little bit more discipline, right? It's not just enough to show up. So you have to learn how to take good notes, how to study, and all that. And I had some trouble with that when I was a sophomore. I got bad grades. I didn't go to class. But then I got my act together, and I kind of figured it out. I got some good classmates. We studied together and supported each other. And after that, I was pretty successful. Like my grades are better. Like I enjoyed school more. So for me, that was probably the most difficult part, because once we figured that out, like my senior year of college was fine. There were some really difficult classes, but like nothing that we couldn't handle. And same thing when I went to work on my PhD. It was the challenge wasn't the difficulty of the classes. It was the challenge wasn't external. It's really internal, right? Like at least for me it was.
Okay, so let's be honest here. Did any like skills from high school transfer over well to college?
From high school, I would say there were some, yeah, that were like being able to think like critically. For the sciences, like it seems kind of weird, but like spatial reasoning, like if you have like a physics or math problem, like that's maybe like three-dimensional, like being able to picture it and visualize what's going on. But critical reasoning, mathematics, like your mathematical skills, if you're going into the sciences, are very necessary. So from my background, I would say those, like being able to read like independently, because when you get to college, you'll have some really dense textbooks, and you'll have to read them and reread them and reread them. I would say probably those. And lastly, like communication, I think is important. And I try to emphasize that in my classes too. And it's basically being able to figure out the answer is not enough. But you have to be able to like communicate. Because no one cares if you've solved this really cool problem if you can't explain what you did, right? And so communication, I think, is important too. And so like working in groups, being able to talk about questions and problems and puzzles, things like that, I think is very helpful. Even in STEM, you would think, why do I have to communicate, or why do I have to do this? It's very important.
So what sparked your interest in astronomy?
I don't know, to be honest, but when I was young, I always liked reading. I read a lot of books on science and mathematics, and I wanted to. I think that's probably what got my interest in like astronomy and astrophysics. Just like reading. I grew up in Providence, Rhode Island, which is a mid-sized city, and there's a lot of light pollution, and you can't see anything, right? So it was kind of my interest was mostly like in the books, like what was possible out there. And for a time, I kind of thought I wanted to be an astronaut, but then my eyesight is bad, and at the time you couldn't be an astronaut if your eyesight was bad. And then I went to college, and my school did not have astronomy, or so I studied physics, and that's kind of where I ended up here. But like what started it was probably just like reading. I don't know. I probably should know that, right? What started this? But I remember reading since I was very young, and I always read books about science and so forth.
Is there a particular book that was really memorable for you, like an astronomy book, Stephen Hawking maybe? I don't know, something that comes to mind that you would recommend to anybody interested in astronomy?
Nothing off the top of my head, but because that was so long ago, I can't remember. But I could probably dig in the cobwebs here and come up with a list, and I could email them to you or so. But I remember going to the library and going to the science section and just like reading everything there. So I don't know if there was just one particular book, but like many different ones.
All right, so Martin, before he has to leave, he wants to know, like pretty bad, what you would say to someone who genuinely believes the Earth is flat.
Oof. That's probably the toughest question. Um, I I'm not sure that they would be able to be convinced, but I would say so they genuinely believe the earth is flat. Um
I feel like I failed you, science teacher, if you believe that.
I know, no, my dad is a flat earther and he like genuinely, he tells me stories and I'm like, that's not how that works.
I mean, I would say like you can go that you can just like go and to the space station. You don't have to go very far up, and you can see like the curvature of the Earth. But then they have explanations for that too. So that probably wouldn't be enough to convince him.
Kind of a
But
lose conversation is what you're saying.
yeah, exactly. But I mean, we knew um ever since the ancient Greeks that the Earth was round. Like I forget the names of but there's a story where these Greeks knew that if they put a post in the ground at this town, at midday the sun wouldn't cast a shadow, but they knew that at this city a few hundred miles away, that post would cast a shadow there, and by doing just some geometry, like they could calculate how big the Earth was.
Right.
Um, but how do you convince them that it's not flat?
Maybe you could just yell at him.
Just,
That's frustrating.
yeah, I would say show them pictures of the Earth from space. It's obviously round, and but then they would probably say, well, that's just a disk, and I'm only seeing this side of it. So you'd have to show them the Earth and the Earth rotating. You can also say, during a lunar eclipse, the shape of Earth's shadow on the moon is a curve. All right. So if the Earth were not a sphere, you would have a different shaped shadow on the moon. But I'm sure they have an explanation for that also.
Right.
I haven't heard that one before. That's good.
Yeah. So when you look during a lunar eclipse, the Earth shadow is curved, right? So you could try that on him. Right? So,
We have about 10 minutes before we have to kind of wrap up because some of our members have to take an activity bus.
Okay.
We have some questions, so I'm gonna go first. Yep. I'm gonna have to be a little bit louder, maybe move closer.
Okay. So, how exactly does gravity work? Like, okay, when you are describing gravity, it describes a 2D plane. How is that when it's all around something, when it's pushing something in?
So say that again.
Like, okay, with gravity, it's always described as it's warping space and time around it. How does it work?
It's hard to visualize that way. The way I explain it to my students is like mass and energy, it bends space itself, right? And when you try to move in what you think is a straight line, that's actually bent. That's actually a curved path. So like imagine you and like a friend of yours starting at like the equator, right? And you're both facing north. And you start maybe a few meters apart. What happens as you guys walk north is you're walking straight north, they're walking north, and you guys think you're walking on parallel lines. But eventually, as you get closer and closer to the North Pole, what you thought were parallel lines are actually going to cross at the North Pole. Do you see that?
Yeah.
And so what you and your friend thought you and your friend thought you were walking on straight lines that were parallel, but as you approach the North Pole, you realize that you're getting closer and closer, right? And so if you've taken like a first semester physics class, you would say, well, there must be a force pulling us together, right? And then, you know, as we approach the North Pole, we're gonna hit each other at the North Pole. And so this is what like the main lesson from relativity is that you think if these people are walking on a curved surface, right? Is there really a force between them? No. All right. They're only moving towards each other because they think they're walking on straight paths, but the paths are bent because they're on a curved space. And what relativity says is, well, we think gravity is a force, but really it's not a force. It's due to the space around us being curved. And when you think you're moving on a straight line and you're being deflected by the force of gravity, it's really that you're moving like in a curved space, like someone on the surface of the earth. So that's how I usually talk about it. That gravity is not a force, it's geometry, right? I don't know if that muddled things more than it helped, but
Yeah.
Yep, got the thumbs up. I've got another question. And then we'll probably have to wrap up after this question.
All right, so my question was, do you think life on Mars will ever be possible?
I think so that's a yes or no question, right? And I think my answer is yes. I think there may be life on Mars, but is it complex life like us with cities and technology? Probably not. No. We would have seen it by now. We have like a whole fleet of satellites photographing Mars and rovers on the surface. I do think though that there may be life, but it would be, if there is, it would be underground, and it would be like simple like life, like bacterial life or something like that. I don't think there is complex life like animal life or like plant life on Mars. But Mars, we know billions of years ago had a big ocean covering almost half the surface. And most of that water was lost to space. But we have discovered water under the surface still. So there's still liquid water under the surface. And I would be willing to bet that there's probably bacterial life somewhere underground. So life in that sense, yes. But we don't know until we go there and do the experiments there.
Any other questions? We have time maybe for one other short question. All right, go for it.
Okay, if a black hole has infinite mass and density, could that make a singularity?
Well, it can't have infinite mass, but a black hole, as far as we know now, it does have there is a singularity at the center, but it's a singularity mathematically. Like what happens is that general relativity breaks down at the very center of a black hole. And what that means is that Einstein's equations can't tell you what happens there. And so we need something else, like a more fundamental theory. And some people are working on that. But there is a singularity at the center, but what it means is that it's just the laws of physics don't tell us what happens at that point. But this is true of all black holes, right? Even a black hole the mass of the sun, or what they call like a micro black hole. You always have a mathematical singularity at the center. And the problem there is that relativity is not enough. You need the physics of the very small. You need quantum physics to describe what happens there. And when you try to combine physics, quantum physics and relativity, they don't get along. And so, but there's people trying. That's part of what my PhD research was on, and there's plenty of people trying to solve that. But the short answer is we don't know. But let me show you one thing here. If I could figure out how to share my screen.
I think I have to give you, I have to make you co-host, I think. I'll do that really quick.
Okay.
All right, you should be good now.
Oh, okay. If you look here, can you see this screen?
No, not yet. Let me double check to make sure it's not on my end here.
Oh, I'm sorry. I needed to do one more step here. Hold on. Oops. There's multiple steps that you have to do. Okay, hold on. Okay. Did that work?
Looks like it.
Yeah. So this is a picture of a black hole, and like I said, this is so you see this like shadow here. This is the black hole, because but when you see this glowing material around it, this is the gas that's falling into the black hole. It's like it's spiraling in, and it gets heated by the tidal forces of the black hole's gravity. And so the gas, when it's superheated, it emits bursts of X-rays and other radiation, and that's what telescopes can pick up. So this is called the Event Horizon Telescope. So they connected a bunch of radio telescopes together to image a black hole. So what you see is the hot gas around it, but you don't see the black hole itself, right? Here it's kind of fuzzy because the resolution isn't that great, and there's material in front of it and behind it. But when people say we have imaged the black hole, this is what they mean. And this is what I was trying to say earlier, where like if someone's standing in front of a bright light, you see their silhouette, like you see their shadow, but you don't see that person. This is kind of like the same thing here. I just wanted to show you that real quick before we finish.
Thank you.
All right, well, thank you so much. We genuinely appreciate your time. Would you mind if I shared your email address with some of our members if they had maybe a follow-up question that we didn't have time for?
No, that would be great. Like, thank you. Like this is really fun.
All right, well, again, thank you very much. We appreciate it. Thank you so much.
Thank you for the invitation.
All right, take care.
Thanks, you too.